n is a positive integer, and we need to show that this inequality is true. This proof requires a classic technique, which is called padding with 1. And this goes hand in hand with the AMGM inequality. What this means is that if you add 1 to a set of numbers, you can increase the number of terms, right? Because you inserted a new element, but you wouldn't change the product because multiplying by 1 doesn't change a product. So here is the first step. We want to apply the AMGM inequality to a set of n plus 1 positive numbers. And we want to create this expression. We want to make the 1 plus 1 over n to the nth power appear. So how can we choose our n plus 1 numbers? Well, let's create a set of numbers. In this set of numbers, we have a bunch of 1 plus 1 over n's. And how many of them are there? Well, there's going to be n copies. And finally, we're going to insert a 1 in this set as well. So there's one copy of the number 1. So what happens when we calculate the arithmetic mean of this set? So this set of terms is going to be the terms that we apply the AMGM inequality onto. We know that AM is greater or equal to GM. So what's the AM of this set? Well, we're going to add them all together, which is n copies of 1 plus 1 over n plus 1. All of that over the total number of terms. There's a total of n plus 1 elements. This must be greater or equal to their geometric mean. The geometric mean is, there's a radical symbol, and it's to the n plus 1th root. And under it, we multiply the 1 plus 1 over n's together. There's a total of n of them multiplied together. And we multiply a 1 in the end. Let's go ahead and simplify. So for the arithmetic mean side, we simplify the parentheses, and we are left with n plus 2 over n plus 1. This we can just rewrite as 1 plus 1 over n plus 1. Is greater or equal to, we have 1 plus 1 over n to the nth power. But we can rewrite the radical symbol as to the 1 over n plus 1th power. Now you can definitely guess what the next step is. Because we know that 1 plus 1 over n, this part is positive, we could go ahead and take the n plus 1th power of both sides. So let's go up here. We have 1 plus 1 over n plus 1 to the n plus 1th power is greater or equal to 1 plus 1 over n to the nth power. But we want to prove that this inequality is true. This inequality here is very close, but we still have to deal with the symbol. Can it be a greater or equal to symbol, or is it strictly greater? Is it possible for equality to hold true? Well, equality only holds if all the terms are equal. So thinking back to our set of elements, each of the elements in the set are the terms that we're dealing with. So in order for equality to hold true, 1 plus 1 over n must equal 1. So is this possible? Well, n is a positive integer. So this equality will never come to be true. 1 plus 1 over a positive number will never equal 1, which means that equality is impossible. So we can just rewrite our inequality as 1 plus 1 over n plus 1 to the n plus 1th power is strictly greater than 1 plus 1 over n to the nth power. So there we have it. We have proven this very symmetric looking inequality. And the main strategy we used in the beginning was called padding with 1. It's where we can strategically insert a 1 into the set of elements that we want to work with in order to keep the product the same, but be able to affect the arithmetic mean. Thank you for watching this video, and I'll see you in the next one.